So has everyone turned in the intermediate project reports? All right. So I'll read through those. It'll take me a while or so, but I'll try and get them back to you hopefully at some point next week with some feedback. So we'll see. So, all right, so the plan for today is to go through a kind of a broad overview of a really cool technique called compressed sensing. And we're going to talk about a fairly simple recovery algorithm called orthogonal matching pursuit, which is kind of the simplest way to do it, and it's not the best way, but it's a very general technique that you'll see applied in all sorts of other areas. And so I realized on Monday that many of you have not really used MATLAB before, and so MATLAB is a really cool tool for dealing with vectors and matrices. And if you try to program like a matrix in like C or something, it's really a pain. But if you do it in MATLAB, it's the language is built to actually to use these things. And it makes a lot of the sort of algorithms that we've been talking about extremely easy. So when I write down these linear algebra things where I'm multiplying matrices together, you just have two variables for two matrices and you multiply them, and it does that for you, right? So we'll go through some examples and kind of see some simple stuff. So and one of the things we'll do is we'll demonstrate this orthogonal matching pursuit running to solve this compressed sensing problem. If I don't show you an example, you might not actually believe it works. So okay, so compressed. Sensing. So the idea. So I'll kind of set it up, and then I'll try and show how it's connected to the other sort of things we've been talking about within this regression section. Hopefully, you'll see it's actually a very connected technique, but it's kind of doing kind of the dual of what we've been doing. So the input is going to be some vector S, and so X is going to be, so say it's going to be a vector in RD. So that means that S transpose is going to look like S1, S2, up to SD, and it's going to be sparse. If I can spell that right, sparse. Okay. So what does sparse mean? It means that most of these values are going to be 0. So almost all of them are going to be 0. There are going to be a few things other than 0 in there, right? So it's, and we'll talk about a simple example where it's all zeros except for a few ones. Okay, so I'll have a running example, and so some of these things don't start working until you get to a fairly large scale because you're using randomness. I'll try and go through a fairly simple example where D is 32, and then we'll actually run this in MATLAB. Doing the calculation on the board is going to be pretty hard here. But so this example, if it's sparse, then you're going to say something like 0, 1, 0. So actually, because we're not going to do exactly, I'm going to probably deviate from the example I have in the notes. What do I have here? 4, 8, 12, 16. Let's do 24. So let's see. So D here, there are 24 values here, and I have 5 ones and the rest are zeros. Okay? So in this example, we'll have that D equals 24, and some M is going to equal to 5. So M is, so this is going to be the number of non-zeros. Okay, so we're going to have some sort of sparse signal. Okay, so when we have data like this, so think of if this is kind of if you're tracking people who have reviewed different movies, you have this huge catalog of possible movies on Netflix, and most people have seen a very small percentage of them. So if they've reviewed them, maybe there's a value between 1 and 5 based on their score for the ones they've reviewed, but most of them are zeros. Okay. So another possible example is, let's say that this is a vector, but it's really describing an image, right? So this image, maybe looks like this, and you have all these pixels. Okay, and so if there's 64 things, then maybe this is 8 by 8, but you can imagine this being much, much, much bigger, right? So you have these really high resolution cameras. So think of if you're taking a picture of the stars under normal conditions. Under certain conditions, probably a lot of these squares are kind of black, and only in some squares you actually see these pixels. You actually see a star, some light. So it's mainly sparse with this actual data, right? If you have a really long exposure in the Milky Way, it's not going to be quite so sparse unless your resolution is really fine. But you can think of there only being a few of these which are filled in. So there are also some more kind of subtle ways where you get these sparse inputs. There's ways in when you're taking pictures just with the regular camera, the image is actually going to look very, very dense. Every pixel is a different color, and you want to capture this, right? Even the wall is white, but it's not quite white. There's some values in there, and so it's not really sparse. But the difference between two pixels is usually going to be, very small. So the difference might actually be very sparse. There's actually only information on the edges between different objects. So your input is going to be the sparse signal. Okay, so this is what your input looks like. A large number of elements, a small number of actual things. And the goal is going to be to take a very small number of measurements of the signal, many fewer than D, and recover where all the ones are. Okay? So the goal is fewer than D so fewer than D measurements, and recover all non-zeros. Okay? So, if you're just measuring, so now I haven't defined what I mean by measurement, right? But the typical way that a camera will work is it measures, it looks at one pixel and it records the value, right? So if I haven't taken the picture yet, I don't know whether it's going to be a 1 or it's going to be a 0 until I actually, go ahead and measure on that pixel. So how can I recover all the ones without testing each of these different values? So I want to measure many fewer than D of these, but recover all of the ones. Okay, so that's where you get this idea of compressed sensing, because you're not going to sense every element individually. You have to somehow compress these measurements and still recover where all the ones are. Okay, so this, Okay, and the trick to doing this, there are kind of two tricks. The first one is you need to use randomness in the measurement and kind of combine together different of these measurements at once. So you're going to kind of measure several of the pixels at the same time and get kind of an aggregate. And then the second step is to kind of take this aggregate and kind of unspool it to figure out where all the ones are. So if you remember, we did this in the streaming section. We did this count min sketch, right, where we did this hashing, and all of these elements got mapped to maybe only one of these 10 different bins, and you have to do this for the homework, the next homework if you haven't started already. But we're able to kind of query these 10 bins, maybe, and there are 5 copies of them, and recover with some accuracy the count of each of these elements, even though we didn't keep an explicit counter for it. So we're going to kind of use some similar sort of ideas here. Okay, so the kind of the first idea is we're going to use a random measurement. Okay, so I'm going to start with one. So we're going to start with we're going to use some matrix X, which is going to be n times d. Okay, and what we want is that n is going to be much less than d. In fact, n is going to be roughly m times log of m over d. Okay, so I'm going to, the number of rows of this matrix is going to be roughly the number of non-zeros I have. So I have very few non-zeros. That's roughly how many rows in the matrix I have. Now this matrix is going to be much bigger than the signal. And I'll mention kind of how this is not really a problem with some examples after I kind of illustrate how this works. Okay, so you're going to get some measurement, y, which is going to be this measurement matrix times the transpose of the signal. And so how's this going to work? Well, so y is going to be this is going to be this vector. Okay, it's going to be a vector of size n. Hopefully I have all the dimensions right here. And so this is an n by d matrix, and this is a signal of length d. So now I'm having these n measurements, and n is going to be much less than d. Okay, so, and then if we look at one element of this vector, this is going to look like one, one row of x times S transpose. And so we're going to write down a row here of X that's going to be the same length as S. Okay? And so X is going to be these random measurements. Every Xij, so in this matrix is going to be uniform randomly at -1, 0, and +1. And there are variations on what you can do here, but you can use this randomly. Okay, so if we write down this measurement, and we just write down one of the rows of this matrix X, this will be Xi, you're going to look something like -1, +1, 0, 0, +1, 0, 0, -1, -1, +1, +1, -1, 0, -1, 0, 0, +1, +1, -1, 0, +1. Okay, so I randomly, probably not randomly, but it's probably it's probably way too regular to be random, but kind of close to randomly generated this random row, this row of X. Okay, so this is one of its n rows. Okay, when I do this dot product, where I do this, this xi dot with S transpose, basically I'm multiplying each thing, each of these together. Right, so this is 0 times something, so it's 0. 1 times minus 1, I get minus 1. 0, 0, 0, 0, 0, 0, 0. Minus 1, 0, 0, 0, 0. Okay, so mainly zeros, and then the dot product adds all these up, and the end result is going to be a minus 2. So this dot product, so this is equal to yi, which is xi dot with S transpose, or multiplied with S transpose. Okay? And so each of these elements in this vector y is one of these measurements. Okay, I'm going to get a small number of these measurements. And now I want to try and recover where all these ones are from here. Okay, so this. So the cool thing is that I only have values where there are actually data here. Okay, so if I look at this green vector here, and I don't actually get to keep this green vector, right? But I keep the sum of it. This green vector only has ones where the original vector has ones. Okay? And so, luckily it turned out, from my example, is that the value I got here was minus 2. Okay, so what's the maximum value, or the smallest value that y possibly, could have been?
Minus n?
No, most could have been minus d, m. Yeah, minus m. Yeah, because it could have been that each of the ones correspond with the minus 1, right? The maximum value could have been m, right? And each of these, every time I pick a random value for one of these, it's randomly minus 1, 1, or 0. So the expected value is 0. So if I get something far away from 0, then the logic is that there are more likely to be ones where my measurement vector has minus 1s. Right? Wherever it has minus 1s, and this is about a third of the locations, it's likely to have these 1s here. More likely than in the other spots. And I've got a set of these. I don't just have one. I've got this n number. And I'll somehow be able to use the set of these measurements to kind of reconstruct where the ones are. And there are these kind of really cool. So if you've taken some linear algebra, this should seem like this is an ill-posed problem, right? So you're trying to recover something that's higher dimensional from data you have, which has fewer. So if you have more variables you're trying to recover, then you actually have these data points. But you can do it because it's sparse. If you assume it's sparse, or actually if it's close to being sparse, then you can get this to work. So you can relax some of these techniques a little bit. If you don't have zeros, but this has a little bit of noise, like 0.01, and then these ones can actually be bigger, then you can still apply this to sort of recovery. So if there's a little bit of noise, this can still work to some degree. But we somehow need to take these measurements and all we get are these values like this -2 and the red matrix, the red row, and recover this S. Okay. Okay, so this is the setup of the problem. This is kind of the specification of how these things typically work. And this is the simplest form of it. There are some more complicated forms. So I'll try and get to soon how you would actually go about trying to recover this vector S. But let me try and give some examples of where this is useful. So this is a technique that's only roughly like a decade old. No one thought of trying to do this before, and I don't know, if I just describe this to you, you'd say, why would we do this? Well, this seems like a fairly strange thing. So some of the places where this has found application, so one of the famous examples, and you can kind of look up some stuff on the internet about this, is something called the single pixel camera. Okay, so maybe you've heard of like a pinhole camera. Well, that's not quite the same thing. Really, the idea is, if you look at how a camera works, when you see like what the gigapixels of a camera is, well, each of those, so each of, there are all these pixels here, and each of them has one sensor that says the amount of light that it sees. And typically, actually, they group them into these groups of 4 things, and they have 2 things that measure the green light, one red and one blue, and then they kind of figure out how to get the color out of that. Right? But you can think of just black and white as each of these pixels has a light meter that says how much light is coming through towards this pixel, focused by the lens in some way. And so the idea is that you want, instead of doing this, to have a single light sensor, that you're going to take kind of multiple readings with this single light sensor, and then be able to reconstruct all of the values of all of the pixels. So the reason why maybe conceptually that this should make sense is you start off, so who here is into like photography, knows about like raw images and stuff like that? All right, so only one person, okay. But so if you get one of these high-end cameras, when you like these professional photographers and people who get really into this, they'll capture something in RAW. That means it saves, in addition to some other stuff, the value from all of the pixels. But if you have a snap and shoot, or you're taking a picture with your phone, it's automatically compressing this usually into a JPEG, which is a much smaller size than all of these pixels. And for most people, if you're really into this, you can tell the difference. Most people cannot generally tell the difference between a high-quality JPEG and the raw image. If you start zooming in, you can see it, but
So the concept of taking a single light meter and then measuring every pixel is just theoretical, because in reality you can't have that work physically, right? You can't have a single light meter and then move around every pixel and measure the value.
So you could do that if the scene was not changing, right?
Yeah.
Yeah.
But still.
But that's doing that for every pixel. I don't want to do it for every pixel.
Okay.
So I'm going to somehow do something like this random measurement vector to do something else. Okay, and so what they do is they're going to think of having all these pixels and randomly that they have this random mask where some of these are blacked out, and so these correspond with zeros. So no light comes through, and so you randomly black out some of these pixels, and there may be a way where you can kind of invert the amount of light, or you can sometimes do this with just the zeros and the ones without the minus ones, I think. And so you just have half the pixels randomly blacked out, and then you take the sum of all the light coming through with the pixels which are not blacked out. And that's going to give you one value, yi. The amount of light coming through with just with half of the random half of the pixels. So it'll be simpler to kind of think that they'll so what you can do is you can kind of normalize by taking an image with all the pixels at once and get the total light, and then and then that's the average light per pixel, and kind of subtract off, so the average value you get is expected to be 0, and that's how you get +1s and -1s. But so you're going to do this in each of these. This corresponds with an xi, and the sum of these pixels gives you this value yi. So this is one measurement, and you're going to do this some n number of times. So instead of every single pixel, you want to have some these random masks on the pixels, and to then have a small number of these measurements. So as the example I was giving, if you have it in RAW, you have all the pixels, but the JPEG is already good. So why not? Can you directly get the JPEG without using all of the sensors in the camera? Or on the other hand, if you have all the sensors, can you get a higher resolution picture somehow than if you were just using each pixel to just capture a small piece of light? That should, maybe that you think that should be possible, because you should be able to get a higher resolution or a higher quality than just these individual pixels, because most times 2 pixels right next to each other have basically the same value. And if you're, so you should be able to say, well, these are the same. I don't need to sense that twice. I can kind of guess that they're going to be the same most of the time, as long as I can figure that out afterwards. And so they're trying to do this with the single pixel camera. So this was a conceptual idea. People actually built cameras that did this. They've also run some. It's easier to do with the simulation where you have the actual image and then you kind of randomly mask stuff. But people actually built cameras that did this, and they kind of work. So this is not the kind of a crowning achievement of this approach, but this was kind of the cool conceptual idea. Okay. So other places where this has kind of had more of a where people have used something kind of like this, and so I'm not sure if this example they've actually used it or if they've used it in things in a similar setting. But if you think of like the Hubble telescope, okay, so what it's doing is it's this telescope that's up in it's in orbit and sending pictures down to Earth, and the communication cost of the picture is going to be really high, as is. And maybe doing compression of it is as well. But you can kind of send up a code which will kind of encode this random mask, and you know it both in space and on Earth, and then you can just send back this measurement vector, and then on Earth you can decode it, and there's less measurement. I'm not sure they actually use this for the Hubble telescope. It's pretty old now, but I think they've used it in other situations where the cost of communicating the image data is really expensive. There's another place where I know it's been used in doing like MRIs on kids. So when you do like an MRI, you're doing this scan of some part of your body, and how it works is there's some sort of imaging technique that is making multiple measurements, and each of them is kind of noisy, maybe from a different angle, and then they try and reconstruct them. And so if you're doing this as an adult, you're probably mature enough to kind of, they tell you, go in there and try not to move for like 20 minutes, right? You actually have to wait 20 minutes because they take many different of these angles. But with kids, they can't sit still for 20 minutes, and they squirm a lot. And then when you're trying to reconstruct these images, you don't know the object you're trying to measure has moved a little bit. So if you can do it with fewer measurements somehow, and still able to reconstruct it, then this is a lot better. Okay, and so you can't get the same resolution as someone who's standing still, but you can do it in far less time. And so they actually use these sort of compressed sensing techniques for doing measurements of MRIs on kids, and you can do them a lot quicker, but then you have to spend time to reconstruct it. So this is some cool application. So there's also some ways where if there's a small amount of noise in this vector, sometimes you can kind of filter out the noise and say that and snap all these to zeros without actually measuring them. So there's several other cool applications. So I don't know all of them, but there's been a lot really kind of very cool area of research, at least in the last decade. Okay. So are people clear on the concept of what we're trying to do here? We have this very sparse signal where we don't want to measure every pixel or every value. We somehow want to take these random masks, these random measurements, and get out just a short vector and then recover the signal. And so you can typically do it, there are techniques to do it where it's so n is actually, there's some constant in front here. And there are some theoretical techniques that say in some situations there's like a constant 4. For different techniques you need like a larger constant. And there's been work on kind of more computationally intensive techniques that reduces this constant in front. I'm going to be talking about the simplest technique, which I think needs a constant of like 20 to kind of have some guarantee of this working. But it'll be a little bit easier to explain, and then hopefully I'll be able to show an example here. Okay. Okay, so now our input is going to be this vector y, which is going to be n by 1, and this measurement matrix x, which is going to be n by d, and this is randomly -1, 0, and plus 1. Okay, and we know that y is going to be x times s transpose. Okay, so the goal is to kind of, what we want to do is try and guess which of these elements of S have, which of the elements of S have 1. Okay, and so if you write it like this, really you can kind of think of a picture where this is going to be skinnier. So this is X, and S is sitting up here, and this is equal to, this equal to Y. Okay, and so we're going to have these columns of X, and they're going to correspond with the value S up here, right? So if there's a 1 up here, then everything in this column is more likely going to have an impact on the magnitude of Y. Okay, so, and so if we have a large value of Y, we have a yi value here, that's going to correspond with the row. So if this is large, it's more likely that this row is correlated with the actual signal. Okay? So then the one that's the most correlated is going to be the one that has, so what we'd really like to do is figure out which of these columns is most interesting. And all we have are these large values of y. So what we want to do is find, so step 1 is we're going to do define the column xj, which is equal to the R max. So this is all columns in X of Y sigma. Okay? So what this is saying, I want to find a column that's correlated with Y. So if this has a lot of large, where this has 1, Y is large. Where it has -1, y is small. Where it has 0, y is also small. So if I have two negative things, then the dot product, remember the dot product is you know, the yc is equal to the sum of I equals 1 to n of yi times ci. So if they're both negative, this contributes to this. If they're both positive, it contributes. If either one of them is 0, if this is 0, then it's not going to contribute. So I want to find the column that maximizes this dot product. And this column is going to be my guess of where this 1 is. Okay? So I'm going to find this guess. I'm going to set this gamma j then equal to the r min of gamma of y minus okay, so then I want to minimize. So I want to choose some coefficient. If I multiply this column by x, I'm going to get as close to y as possible. So I had this nice property that because I randomly was -1, 0, or +1, that the expected value of anything in y was actually, of any element in y was actually going to be 0. Or was actually going to be, is going to be, expected value here is going to be, is going to be basically the magnitude of this guy, right? Everything else is going to cancel out. So what I'm going to do is try and find the scaling of this column so I hit y, and all the other columns should kind of cancel out because they're randomly 0, -1, or +1. Okay, and so then I'm going to, you know, essentially I'm going to set Sj equal to this gamma j. So I'm going to solve what I think is the best coefficient, the best explanation of this, and I'm going to set that value here. And maybe I'm going to assume that this is 0, 1. So if I find this, I always set gamma j equal to 1. That's going to work better if I know these are 0, 1s. Okay. Okay. So but now I've explained part of why doing this. And I've only found one of these locations. So now I want to factor out this explanation. Right, so now I'm going to set